Alternative drive systems such as hydrogen, CNG, LPG, and battery electric power are becoming increasingly common in vehicles. To respond effectively to the specific hazards these technologies pose, whether in accidents or fires, fire services need a tailored and targeted measurement strategy. My name is Ulrich Klink. I'm a training specialist at Dräger, and in this video, I'd like to introduce a practical tool for emergency response teams, the measurement strategy for vehicles with alternative drives. Each alternative drive technology presents unique hazards that must be considered during incident planning. This applies not only to large urban areas or industrial zones, where established protocols for managing chemical risks may already exist, but in any setting where such vehicles are in use. At the same time, the growing number of alternative vehicles has led to an increase in specialized service workshops. These facilities can introduce additional risks during maintenance activities, particularly where undetected gas leaks or fires may arise. Fire and rescue services must be equipped to identify these hazards rapidly and implement appropriate countermeasures. Hydrogen is highly flammable and can form explosive mixtures rapidly in the event of a leak. In enclosed spaces, such as garages or underground car parks, it disperses quickly and explodes with very little ignition energy. Early detection is therefore critical. Specialized gas detection and warning systems enable emergency responders to identify hazardous hydrogen concentrations before ignition thresholds are reached. LPG and CNG are both highly flammable fuels. LPG, being heavier than air, tends to accumulate in low-lying areas where it can ignite upon contact with an ignition source. CNG, in contrast, disperses more readily into the atmosphere, but can still form explosive gas-air mixtures within a short period. In both cases, appropriate gas detection and warning systems are essential. Electric vehicles powered by lithium-ion batteries present distinct risks, particularly during thermal runaway or battery fires. In addition to generating extreme heat, burning batteries can release a range of hazardous gases, including hydrogen fluoride, carbon monoxide, hydrogen, and hydrogen chloride. These gases not only pose serious health risks, but may also contribute to fire or explosion hazards. This risk is especially critical in confined environments like underground car parks or when vehicles are covered with fire blankets. Even in the absence of fire, damaged battery cells can release gases that may form explosive gas-air mixtures. Early identification of these gases is therefore critical, not only as indicators of battery off-gassing, but also as an indicator for immediate protective measures. To address the risks posed by alternative drive systems, we have developed a tailored measurement strategy. It incorporates both electronic gas detection devices and Dräger Tubes. It builds on the measurement strategy for fire services, which has been in use for several years and can be easily expanded to include the measurement strategy for alternative drive systems. The focus is on adapting procedures while maintaining key principles. However, what remains the same is that measurements for explosive atmospheres should always be carried out from the very beginning and ideally continuously. At the core of this approach is the decision tree shown here. First, we begin by distinguishing between the type of drive. Then we assess whether the incident includes a fire component. For incidents without fire, the priority is to detect explosive atmospheres. In these cases, a device equipped with a catalytic X sensor provides fast, reliable warnings. Substance-specific measurements can also be carried out using Dräger Tubes. In fire scenarios, it is primarily the smoke gases that can be detected, for example, using a simultaneous test set designed to identify key substances in accordance with the VFDB. These simultaneous test sets can also be used when batteries are damaged but have not caught fire. This is because the gases released contain most of the same substances as smoke from a fire. In all cases, additional specific electrochemical sensors and Dräger tubes may be used where more detailed measurement is required. However, for initial hazard assessment, a catalytic explosion sensor integrated into an electronic detection device, together with the corresponding simultaneous test set for key substances in accordance with the guidelines of the VFDB, are essential tools for enhancing safety at the scene. Gas detection plays a critical role in the early identification of toxic and flammable substances, and in supporting a timely and effective emergency response. This is particularly important in enclosed or semi-enclosed locations such as garages, workshops, or underground car parks, where explosive gases can accumulate quickly. Rapid detection and effective ventilation are essential to mitigate risk. Through targeted training and the implementation of tailored measurement strategies, fire and rescue services are better equipped to address the operational challenges associated with alternative drive technologies. This not only enhances the safety of emergency personnel, but also protects the public, ensuring prompt, effective hazard control during fires and accidents. Adopting these strategies is a key part of ensuring safety and efficiency in modern emergency response planning.